Welcome to Whispering Scientist. It's really lovely to have you here tonight. Maybe you're listening in a quiet bedroom, the lights already low, your phone resting on the pillow beside you. Maybe you're on a late-night train, watching darkness slide past the window while the carriage rocks you gently. Or maybe you're curled up on a couch with a warm drink, letting the day slowly loosen its grip. Wherever you are, I hope you feel safe. I hope you feel that, for this little while, there is nothing you urgently need to do, nowhere else you urgently need to be. This time is just for you, for your mind to wander, and, if it wants to drift softly into sleep. If you find yourself returning to these calm journeys, you're always welcome to support this sleepy little channel with a like or a subscribe, but only if it feels gentle and easy, never a chore. Think of it as leaving a small, quiet lighthouse on for yourself, so you can find your way back here whenever you need a peaceful night. Tonight, we're going to explore something you've known about since school, and yet, almost certainly, haven't seen in its full, hidden form. You were probably told that matter exists in three main states: solid, liquid, and gas. Maybe, if your teacher was feeling a little adventurous, they added a fourth one: plasma. But this is only the surface. Behind those simple categories, matter has a whole wardrobe of secret outfits it can wear, strange, exotic states that almost never appear in everyday life, but quietly fill the universe with possibilities. What if there were forms of matter so cold, so perfectly calm, that millions of atoms move together as if they share a single mind? What if there were liquids that can climb walls, or currents of electricity that flow without losing any energy at all? And far in the other direction, what if, for a tiny instant, matter becomes so hot and so intense that the particles inside protons and neutrons are set free, like a glimpse of the universe in its very first moments? Don't worry, you don't have to memorize any of this. You don't have to pass a test or solve a problem. You can simply let these ideas drift past like clouds, some sharp, some soft, some already fading by the time they reach you. As we wander through this story, we'll move very slowly. We'll start with the familiar, the solid mug, the liquid tea, the gentle steam rising into the air. And then, one step at a time, we'll slip into the hidden states, glowing plasmas that fill the stars, ultra-cold quantum puddles that behave like a single wave, and fiery primordial soups that once filled the newborn universe. Along the way, I'll invite you to imagine simple pictures: marbles in a box, people dancing, ripples on water, mugs and blankets, and breath on a cold window. No equations, no frantic science class energy, just calm images, one after another, like pages slowly turning. If, at any point, something sounds confusing, that's perfectly okay. In fact, that's expected. The goal tonight isn't to tame every mystery, it's to rest beside them, the way you might sit quietly beside a lake at night, watching ripples you don't need to explain. You might notice your eyes growing heavier, your breathing slowing down. You might miss whole sections of this story and then return to it as if waking from a dream. That's not a problem. This is a science story designed to be half remembered, half slept through. So, as you settle in, maybe adjust your pillow or your headphones, feel the weight of your body where you're resting, and let the day move a little further away. In a moment, we'll begin with what you already know: solids, liquids, and gases. The ordinary states of matter that quietly shape your room right now. The bed beneath you, the air around you, the water in your glass. And then, as we go on, things will become just a little stranger. But don't worry. We'll move gently, step by step, into the hidden states of matter that have been there all along, waiting, like secret chapters in a book you thought you'd already finished. Whenever you're ready, we'll take our first slow step into that story. Before we wander into the strange, hidden states of matter, let's rest for a while with the ones you already know. Sometimes, the best way to understand the mysterious is to begin with the ordinary and notice that it has been quietly mysterious all along. So, picture this. You're lying in bed. Next to you, on a small table, there's a mug of something warm. Maybe tea, maybe hot chocolate, maybe just water that's been warmed until it gives off the faintest little curls of steam. In that tiny scene, you can already see three familiar states of matter. The mug itself is a solid. It keeps its shape. If you pick it up, it doesn't sag or slosh or spill. The liquid inside the cup is, of course, a liquid. It flows. It takes the shape of the mug. It shivers gently if you nudge the table. And the faint steam rising from the surface, or the invisible air around you, is a gas. Very normal, very everyday. Nothing shocking at all. But then things get a little more interesting. Not louder, not wilder, just quietly deeper. If you could somehow shrink down, not just to the size of a grain of sand, but far, far smaller, smaller than dust, smaller than the tiniest speck you can imagine, you would see that each of these states is really just a different style of motion. You might imagine the particles in a solid like people, standing in a tightly packed crowd at a concert. They don't have much room to move around. They can sway a little, shuffle, vibrate in place, but they don't easily swap places with each other. That's your solid mug, trillions upon trillions of particles, all locked into a kind of organized grid, each jiggling in a tiny space, but staying where it belongs. Now, think about the liquid in the mug. Here, the particles are more like people at a relaxed party, walking around a living room. They can slide past each other, rearrange, drift across the room. They're still close together, still feeling each other's presence, but no one is stuck in a fixed seat. That's your liquid. Atoms and molecules moving more freely, flowing, able to pour from one place to another. And then, the gas, the air in your room, or the steam rising from your drink. This is more like people scattered through a huge park, running and wandering almost wherever they like. The particles are far apart compared to their own size, zipping around, bumping into each other, and then flying apart again. That's your gas, spread out, energetic, filling whatever space is available. If that sounds a bit odd, don't worry. You don't need to track every detail. Just hold on to a gentle idea. Solids, liquids, and gases are the same kind of stuff, just dancing in different ways. Now, here's the part that quietly breaks our usual thinking. These states aren't fixed labels that belong to certain substances forever. They're more like moods. Water can be solid ice, flowing liquid, or invisible vapor, and it's still water each time. The difference comes from energy, especially in the form of temperature. You might imagine temperature as how energetic the dance is. When it's cold, the music is slow, and the dancers hardly move. When it's hot, the music speeds up, and the dancers dash, spin, and collide. So when you heat a solid, you're turning up the music. The particles, once mostly shaking in place, begin to move more strongly until, at some point, they shake themselves free of their fixed positions. That's when a solid melts into a liquid. Keep heating that liquid, and eventually the particles get so energetic, so eager to move, that they break free from the surface altogether. They don't want to stay together in a puddle anymore. They want to roam the whole room. That's boiling, the liquid becoming a gas. And if you cool things down, you're slowly turning the music down again. Gas particles slow until they can't wander as far. They condense into a liquid. Cool them further, and they settle into the tight, orderly crowd we call a solid. It all sounds very neat and tidy. But even here, with the everyday states, there are quiet complications. Not all substances behave in exactly the same way. Some change state at higher temperatures, some at lower. Some skip steps under the right conditions, going straight from solid to gas, like dry ice. You don't have to remember the details. Just notice the idea. Changing a state of matter is less like changing the substance itself, and more like changing its pattern of movement. In a way, your room right now is a little theater of phase changes. The warmth of your body is gently heating the sheet beneath you. Your breath carries tiny droplets of water from inside you to the air around you. The mug on your bedside table might slowly be cooling, its steam fading into the room, its liquid eventually coming to rest at the same temperature as everything else. All of this is happening without any drama. No one announces, the liquid is now becoming a gas. The universe just quietly rearranges itself, particle by particle, according to how much energy is available. If you like, you can imagine little labels floating next to your belongings. Solid on the wall, liquid on the drink, gas on the air. But those labels would need tiny footnotes describing all the ways those states can change with temperature and pressure. In a moment, we'll let those labels loosen even more. Because solid, liquid, and gas, as familiar as they are not the whole story. They're like the first three colors in a paint box. Useful, important, everywhere, but not the full palette. Soon, we'll drift into a state of matter that's so energized it glows, where atoms are torn apart into charged pieces, and the gas itself becomes a conductor of electricity. You've seen it in lightning, in neon signs, and in the very stars above you, even if nobody told you its name. But don't worry, we'll move toward it very gently. For now, you can just lie there, feel the solid support beneath you, the softness of any fabric touching your skin, the coolness or warmth of the air sliding past each breath. Solids, liquids, gases, old friends, quiet, familiar, and already more mysterious than they first appeared. Now that we've spent a little time with solids, liquids, and gases, let's let things warm up just a little. Not in your room, don't worry, just in your imagination. You can keep your blanket exactly where it is, your pillow exactly under your head, but in your mind, we're going to turn the temperature up so high that the ordinary rules of gas begin to melt away. Think back to the air in your room. We said a gas is like people wandering freely in a big park, bumping into each other now and then and drifting apart again. If we slowly make that gas hotter, the particles move faster, zipping around more energetically. This is still normal gas behavior, but then things get even stranger, in a very quiet, scientific way. Heat it further, far beyond anything you feel on a summer day, beyond the hottest oven in your kitchen, beyond the surface of most planets, and the collisions become so violent that electrons are knocked right off their atoms. Suddenly, the gas isn't just made of neutral atoms anymore. It becomes a mixture of positively charged ions and free electrons. This is no longer an ordinary gas. This is a plasma. You've actually seen plasmas before, even if no one introduced them properly. Picture a bolt of lightning cutting through a stormy sky, that bright, jagged line illuminating the clouds for a heartbeat. In that flash, the air along the lightning's path is turned into plasma, a hot, ionized gas that conducts electricity and glows. Or imagine a neon sign outside a cafe at night, casting a soft, colorful light onto the pavement. Inside the tubes, a gas has been energized by an electric current until it too becomes plasma, shining in reds, blues, and greens. And of course, the biggest, most persistent plasma you see, even if you don't look at it directly, is the Sunday. Our star is a vast ball of plasma, its atoms stripped and stirred, held together by gravity and shaped by magnetic fields. If an ordinary gas is like a crowd of individuals, all doing their own small random walk, a plasma is more like a crowd that suddenly starts paying attention to the music of electricity and magnetism. The charged particles don't just move randomly, they respond to electric fields, loop around magnetic field lines, and sometimes form beautiful, filament-like structures and glowing arcs. You might imagine a plasma as a kind of electrically active fog, where every tiny drop is charged and sensitive to invisible forces. Or like a school of fish that suddenly starts swimming in swirling patterns, each one responding not only to its neighbors, but to currents in the water that you can't see. Most of the matter we encounter on Earth's surface is not plasma. Your pillow, your blanket, your skin, the mug on your table, they're all mostly solids, liquids, and gases under calm conditions. But if you step back and think of the universe as a whole, the balance shifts. Out there, between and inside the stars, in the thin, hot gas that fills galaxies and clusters of galaxies, in stars themselves, in flares and jets and auroras, plasma is everywhere. By some estimates, most of the visible ordinary matter in the universe is in the plasma state. It's a strange thought. The everyday states that feel so normal to you are, on the cosmic scale, almost a kind of exception. Cool, quiet islands in a universe of fiery, ionized seas. You don't need to hold on to the numbers or the details. Just a soft idea is enough. When gas is heated enough, atoms can lose their electrons, and the whole collection of particles becomes charged and responsive to electric and magnetic fields. That's plasma. Plasmas can behave in ways that ordinary gases don't. They can carry electric currents and generate magnetic fields. They can twist and knot into complex structures. When you see images of the sun with great looping arcs rising from its surface, those arches are shaped by magnetic fields guiding the flow of plasma. In your mind, you might picture a glowing, translucent ribbon rising from the sun's surface, curling and looping like a slow-motion wave in the air. The particles that make up that ribbon aren't just drifting aimlessly. They're winding along a magnetic path, like beads sliding along invisible wires. If that sounds a bit complicated, that's okay. You don't need to solve the equations that describe it. You can just imagine a bright, slow, molten-looking loop of light moving to the music of forces you can't see. Here on Earth, scientists trap plasmas inside special machines, donut-shaped devices called tokamaks, and other designs that try to hold the hot, charged gas in place using strong magnetic fields. Why? Because if we can tame certain kinds of plasmas, we hope to unlock controlled nuclear fusion, the same process that powers the sun, as a potential source of energy. You might picture such a device as a kind of artificial star in a ring, a glowing halo of plasma held off the walls by magnetism, never touching the container directly because it is far too hot. It's a bit like trying to hold a sunbeam in your hands without getting burned, except instead of hands, we use magnetic fields. And instead of a sunbeam, we use a little torus of star-like plasma. But even outside of grand scientific projects, plasmas touch your life in smaller ways. The soft glow of fluorescent lamps, parts of the screen technologies, the auroras dancing near the poles of our planet, all of these involve plasmas. Auroras, for instance, happen when charged particles from the sun interact with Earth's magnetic field and atmosphere, creating shimmering curtains of light. You can picture them as the sky's way of whispering back to the solar wind, turning the invisible story of charged particles into visible, flowing color. If you feel your mind wandering, that's perfectly fine. You might just hold on to a single image: a night sky, a curtain of green and purple light rippling in slow motion. Somewhere above that, the thin air has briefly become plasma, glowing as if the atmosphere itself has decided to paint. And here's a gentle twist to keep in the back of your thoughts, if you like. Plasma isn't always wild and explosive. Sometimes it behaves like a surprisingly smooth fluid with its own waves and ripples and quiet flows. In many ways, it's just another pattern that matter can fall into, given enough energy and the right conditions. So, when you hear the word plasma, you don't have to imagine something terrifying or out of reach. You can think of lightning, neon lights, the sun, the glow of auroras, all reminders that matter, when it's energized enough, becomes not just hot, but electrically alive. In a moment, we'll gently turn the temperature dial the other way. We've seen what happens when we heat matter so much that it tears itself into charged pieces and glows. Next, we'll quietly explore what happens when we cool matter down, 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 almost to complete stillness. Because if plasma is matter in a kind of energetic storm, then the hidden states, waiting at the other end of the thermometer, are like matter in meditation, so calm and so cooperative that countless atoms can begin to act as one. For now, though, you can stay exactly where you are, wrapped in your own calm, feeling the ordinary states of matter around you. The solid bed, the liquid in your body and in your glass, the gas of the air that fills your lungs. Somewhere far above, the sun glows as a giant ball of plasma. Somewhere else, lightning may be stitching brief lines of brightness in a distant storm. And here you are, safe and small under your blanket, listening to stories about the secret lives of matter. When you're ready, we'll let the temperature fall and watch what happens to matter when the dance of its particles slows almost to a whisper. Now that we've let matter burn itself into star-like plasma in our imagination, let's do something gentler. Let's slowly, quietly, turn the dial the other way. You can think of this chapter as a slow exhale for the universe. We've seen what happens when everything is heated into a kind of brilliant storm. But what happens when we keep cooling and cooling and cooling until the storm is almost gone? If that sounds a little strange, don't worry. You don't need to follow every step. Just drift with the idea. We're about to watch the dance of particles slow almost to a stop, and then discover that, at the very edge of stillness, something beautifully unexpected appears. Take a moment to notice your own body. Maybe one hand is warmer than the other. Maybe the air on your face feels slightly cooler than the warmth beneath your blanket. Without thinking about it, you've been feeling temperature all day. But what is temperature, really? Imagine, again, a crowd of people in a room. When the music is slow, people sway, maybe shuffle a little, but no one is running. When the music speeds up, people dance more vigorously, move faster, bump into each other more often. Deep down, matter behaves a little like that. At the microscopic level, particles are always in motion, jiggling, vibrating, flying, spinning. Even in a solid, where everything looks stable and still, the atoms are trembling in place, like people standing in fixed positions, but gently bouncing their knees to a silent rhythm. Temperature, in simple terms, is a measure of how energetic that microscopic dance is. When something is hot, its particles, on average, are moving more energetically. When something is cold, they're moving more slowly. You can picture a hot object as a restless crowd and a cold one as a drowsy gathering, where everyone is almost nodding off. Now, here's where the quiet mystery begins. If temperature is linked to motion, you might wonder, what if we keep cooling something down all the way until the particles stop moving completely? Can we reach a place where everything is truly, absolutely still? Physicists have a name for the lowest possible temperature, absolute zero. On the Kelvin scale, which starts at this bottom point, absolute zero is 0 K. On the more familiar Celsius scale, it's 273.15 degrees Celsius. It's an unimaginably cold state, far colder than any winter day on Earth, far colder than the emptiness of interstellar space. Absolute zero, in our best understanding, would be the point where the particles of a system have as little thermal motion as nature allows. But there's a soft catch. According to what we've learned about the quantum nature of the world, the rules that govern extremely small things, particles, can never be completely, perfectly still. You can think of it like trying to pin down the exact position and exact motion of a tiny object at the same time. Quantum mechanics tells us there's a fundamental fuzziness there, a kind of built-in uncertainty. The particles can't simply sit, motionless, in a perfectly defined spot. They always retain a tiny, irreducible jitter, often called zero-point motion. So, in practice and in theory, absolute zero is like a horizon. We can get closer and closer, but never fully reach it. We can dim the music to an almost silent hum, but the universe doesn't quite let us turn it fully off. If that feels slippery, that's okay. You don't have to nail it down. Just hold on to a gentle image. No matter how much we cool a system, its particles always have a little bit of built-in quantum quiver left. Still, scientists have become incredibly good at cooling things to temperatures unimaginably close to that horizon. You might imagine a series of steps. First, they cool gases with traditional methods, letting them expand or contacting them with colder surfaces. Then, they bring in more delicate techniques. One of the most beautiful is called laser cooling. At first, that sounds backwards. Lasers often make us think of heat and cutting and burning. But here, lasers are tuned in such a way that they can gently slow atoms down. Imagine you're trying to slow a spinning toy car by repeatedly tossing tiny, soft ping-pong balls at it from just the right direction. Each ping-pong ball that hits the car steals a tiny bit of its speed. In a similar way, when atoms absorb and re-emit carefully chosen photons of light, their motion can be nudged over and over until they're moving much more slowly, cooled to incredibly low temperatures. The details involve careful tuning and quantum rules, but the feeling you can keep is this. By using light itself very cleverly, scientists can gently calm the motion of atoms, like lulling them towards sleep. Beyond laser cooling, there are other tricks, magnetic traps, where atoms are held in place by magnetic fields, and evaporative cooling, where the most energetic atoms are allowed to escape, leaving behind a calmer, colder group, just as steam escaping from a hot cup of tea leaves the remaining liquid cooler. All of this effort is aimed at bringing certain collections of atoms to temperatures just a whisper above absolute zero. At these ultra-low temperatures, something important happens. The ordinary chaos of thermal motion, which usually hides quantum behavior, fades into the background. The noise of random jiggling becomes so quiet that the underlying quantum music can finally be heard. Under everyday conditions, the atoms and molecules around you are acting according to quantum rules too, but their behavior is buried under the roar of thermal energy. At very low temperatures, that roar becomes a murmur. It's as if we're used to watching a crowd in a storm, rain and wind obscuring any fine details. But when the storm calms and the last drops fall away, you suddenly notice subtle patterns you couldn't see before. At these near-zero temperatures, particles stop behaving like little marbles and more like waves that can overlap and blend. You might think of each particle not as a precise dot, but as a fuzzy cloud, with a wavelength that describes its quantum spread. As things get colder, these wavelengths grow longer. At ultra-low temperatures, the fuzzy clouds representing different particles can begin to overlap, merging into something new and collective. This is where the story begins to bend away from the everyday. At room temperature, Each particle in a gas is like a separate dancer, moving on its own path, even if the dance floor is crowded. At temperatures close to absolute zero, especially for certain kinds of particles, those dancers can begin to fall into step, not just in rhythm, but in their entire state. Many particles, in a sense, can begin to share the same identity, acting less like a big group of individuals and more like a single entity spread out in space. If that sounds like science fiction, remember, you're not required to fully understand it. You can just imagine something gentle and strange. A cloud of atoms that forgets it is made of many parts and behaves instead as if it were one continuous, shimmering piece. To reach these conditions in the lab, scientists create carefully isolated, tiny clouds of atoms, often alkali atoms, like rubidium or sodium, and cool them with lasers and magnetic traps. They measure temperature not by how it feels to the hand, but by how fast the atoms are moving, by the patterns of light they absorb and emit, by the shapes of the clouds they form. As the temperature drops into the billionths of a degree above absolute zero, the old, familiar identity of a gas begins to melt into something new. We are edging up to a quiet threshold. On one side of that threshold, we have a very cold gas, whose atoms, though slow, still behave like separate particles. On the other side, we have a new state of matter where many of those atoms share a single, unified quantum state, a collective wave, a kind of superatom built from many individual ones. This new state is called a Bose-Einstein condensate, and we'll spend time with it soon. For now, it's enough to know that all our talk about cooling, temperature, and quantum quiet is leading us there. You might think of this point in the story as the moment when the lights in a theater are dimmed almost to darkness. The audience, once noisy and individual, falls into a shared hush. Each person is still there, of course, but something collective emerges. A single, calm atmosphere. In the same way as matter cools and the random jiggles of heat fade, nature reveals something new, not in the noise of many separate motions, but in the quiet of a shared quantum pattern. If your mind is starting to feel a little foggy with ideas, that's perfectly fine. This is the chapter where the details can gently blur. You don't need to remember the numbers, the techniques, or the names. Just keep 3 soft thoughts. First, temperature is about the energy of microscopic motion. Second, absolute zero is like a horizon of perfect stillness that we can approach but never touch. And third, as we get very close to that horizon, the deep quantum nature of matter starts to shine through in new, collective ways. You can, if you like, imagine a tiny cloud of atoms gently floating in a dark, quiet chamber, cooled until their dance is barely there. Slowly, their individual ripples blend together, like overlapping waves on a perfectly still pond, forming one broad, smooth swell. In a moment, we'll step fully into that picture. We'll watch matter become more than just cold. We'll see it turn into a single, shared wave, a state where countless atoms move in harmony as if they were one. For now, just breathe. Feel the slower rhythm of your own body, the quiet around you, the softness of your pillow or the surface supporting you. The universe, in all its fiery plasmas and ice-cold quantum puddles, is still out there. And here you are, resting in the middle of it, listening to the story of how matter behaves when the dance of temperature is turned almost all the way down. Soon, we'll meet that new, hidden state face to face, a condensate where many particles become one calm, whispering wave. Now we're ready to cross that quiet threshold we've been approaching. We've watched the dance of particles slow and slow. We've crept toward absolute zero. And now we're going to step into one of the strangest, softest rooms in the whole house of physics. This is the place where many particles begin to act like one, a hidden state of matter where individuality fades and a shared identity appears. Now here's the part that quietly breaks our usual rules. We're used to thinking of matter as made of countless tiny bits, each doing its own thing. But in this state, the bits agree, in a very deep quantum way, to behave as if they are one. This is the world of the Bose-Einstein condensate. You can stay exactly where you are, lying in bed, resting on a couch, maybe feeling your eyes grow heavier. We're going to take this slowly, like telling a bedtime story from 100 years ago. Imagine a physicist named Satyendra Nath Bose in the early 1920s. He's working on how particles of light, photons, are distributed, following the quantum rules that had just been discovered. He comes up with a new way of counting states for these particles, a way that treats them as a special kind that can pile into the same quantum state without protest. He sends his work to Albert Einstein, who recognizes something important in it. Einstein extends Bose's ideas not just to light, but to matter, to atoms themselves, if those atoms belong to the right family. This family is what physicists call bosons, named after Bose. Bosons are particles that are allowed, by nature's quantum rulebook, to share the same state. They can overlap in the same quantum seat without the usual restrictions. Their cousins, called fermions, like electrons, protons, and neutrons, are more stubborn. They follow the Pauli exclusion principle, which says that no two identical fermions can occupy exactly the same quantum state. They must spread out, each one taking its own slot. You don't have to memorize these names. Just a gentle distinction is enough. Some particles are comfortable sharing, some are not. Bose and Einstein realized that if you take many bosons and cool them down enough, something remarkable should happen. As the temperature drops and the dance slows, more and more of these particles will fall into the lowest energy state available, like people gradually moving into the quietest, comfiest spot in a room. In their prediction, at very low temperatures, an enormous fraction of the particles would all occupy that same lowest state. Instead of a cloud of atoms, each in a different configuration, you would have a large collection of atoms sharing one quantum description. Einstein described this as a new kind of condensation, not droplets of water forming from vapor, but particles condensing into a single quantum state. Hence the name Bose-Einstein condensate. For decades, it remained a theoretical dream. The temperatures needed seemed impossibly low. The control required over atoms was beyond the technology of the time, but science likes to wait patiently. As the 20th century moved on, new tools appeared: better vacuum systems, laser cooling, magnetic traps. Slowly, what once sounded like a fantasy, cooling atoms to billionths of a degree above absolute zero, became possible. In 1995, in laboratories in Colorado and Massachusetts, researchers finally coaxed a gas of rubidium atoms, and later sodium atoms, into this long-predicted state. They cooled them until their individual quantum waves overlapped and merged, creating a new, delicate droplet of matter behaving as one. If that sounds a bit abstract, let's build a picture you can rest your mind on. Imagine a room full of violinists, each playing their own note at their own speed. It's a kind of noisy, complicated sound. That's like an ordinary warm gas. Many particles, many states, lots of disorder. Now imagine that, as the room cools, each violinist, one by one, starts playing the same note in perfect unison, at the same tempo, with the same phase. Eventually, instead of a messy clatter, you have one pure, steady tone filling the room. A Bose-Einstein condensate is like that pure tone. Many atoms, but one shared quantum song. Or if you prefer a visual image. Think of each atom as a small, fuzzy wave. At high temperatures, all the waves are short and separate. They overlap only slightly. As the gas cools, the waves stretch out, becoming longer and more diffuse. At some point, those waves overlap so much that you can no longer tell where one ends and another begins. The result is a single, larger wave, a matter wave that describes the whole collection. In experiments, scientists can actually see signs of this change. When a cloud of atoms is cooled into a Bose-Einstein condensate and then gently released from its trap, the way it expands and the pattern of density they detect shows the imprint of its wave-like nature. Two condensates can even be made side by side, and when they are allowed to overlap, they form interference patterns repeating light and dark bands, similar to what you get when waves of water overlap on a pond or when beams of light interfere. These patterns aren't drawn on a chalkboard. They appear in real measurements, as if the cloud of atoms is acting like a single wave that can interfere with itself. If that feels like too much, you can forget all the technical parts and keep just this quiet thought. A Bose-Einstein condensate is matter behaving like one smooth, unified wave, rather than a crowd of separate particles. Because the particles share one state, the behavior of the condensate can be remarkably gentle and coherent. It can flow in ways that hint at other phenomena, like superfluidity, where friction seems to vanish. In fact, Bose-Einstein condensates are deeply connected to other macroscopic quantum effects. Superfluids, superconductors, and condensates all involve many particles acting in a coordinated, wave-like fashion rather than as independent marbles. Sometimes, condensates are held in special traps made with light, so-called optical traps, where laser beams create a kind of bowl for the atoms to sit in. By adjusting the shape of this bowl, scientists can nudge the condensate into different configurations, making it stretch along one axis, or flatten into a sheet, or divide into separated pieces. You might picture a tiny, ghostly droplet, invisible to your eyes, hovering in a vacuum chamber behind thick glass and polished metal. Laser beams you cannot see hold it gently in space. Within that droplet, tens of thousands, or even millions, of atoms are all part of one shared quantum wave. From the outside, it's quiet. There is no glow, no hum, no obvious sign that anything strange is happening. Only by probing it with carefully tuned light and magnetism do we learn that it behaves differently from an ordinary gas. This is one of the charms of the hidden states of matter. They are not always flashy. Many of them are subtle, delicate, and easily disturbed. They require laboratories and careful isolation because the slightest warmth from the environment can kick the atoms out of their shared state. You can think of a Bose-Einstein condensate as nature's version of a very shy, very fragile pattern. It only appears when conditions are just right. Extremely cold, carefully shielded, gently handled. But when it does appear, it gives us a window into the quantum world at a human scale. Instead of quantum effects hiding in the behavior of single atoms or electrons, they spread out across a whole droplet of matter that we can, in principle, see and manipulate as a whole. Scientists use condensates to study how waves and particles behave in new regimes, to simulate other systems that are hard to probe directly, and to explore possible technologies that might someday use these states for sensing, precision measurement, or information processing. For you, listening now, it doesn't need to be a toolbox. It can just be a story about matter that, when cooled enough, stops behaving like a restless crowd and starts behaving like a choir singing one note. If your thoughts are starting to blur, that's okay. You might only remember that there is a way for atoms to lose their individuality and become a single, calm wave. That somewhere, in dark rooms filled with humming equipment, people coax tiny clouds of atoms into this quiet chorus, just to see how nature behaves when everything agrees. In a moment, we'll see that this idea, many particles moving together as one, doesn't stop with condensates. There are liquids that flow without friction, currents that move without resistance, and other macroscopic quantum states that share this same spirit of collective behavior. But we'll get there slowly. For now, imagine that little ghostly droplet again. A tiny cloud of atoms, so cold that they've fallen into one shared state, their waves overlapping until they're practically indistinguishable. It is still made of many particles, and yet, in another sense, it is one thing. You can let that image drift to the side of your mind, like a strange but gentle dream. You don't have to solve it. You don't have to fit it neatly into your everyday experience. Just know that, beneath the solids and liquids and gases that feel so familiar, there are hidden ways that matter can organize itself. Some are fiery and wild, like plasma. Some are quiet and cooperative, like a Bose Einstein condensate. And in the chapters to come, we'll follow that idea of cooperation further into liquids that refuse to slow down and materials where electricity flows as if friction has disappeared, superfluids and superconductors. More members of this quiet quantum family. If your eyes are heavier now, that's perfectly fine. You can drift, half listening, half dreaming, as we move from this calm, shared wave of atoms to the flowing, frictionless worlds that it helps us understand. Now that we've met this ghostly Bose-Einstein condensate matter as a single, calm wave, let's follow that quiet idea into something you can almost picture as a liquid with a personality. A very strange personality. Now here's the part that quietly bends the rules again. We're used to the idea that liquids flow, but they also resist flowing. They have viscosity, a kind of internal friction. Honey flows more slowly than water. Oil feels different from juice. Even water will eventually come to rest if you stop stirring it. But there are liquids in nature that, under the right conditions, seem to ignore that rule. They can flow through tiny channels that would block ordinary liquids. They can climb walls. They can swirl in circles for a very, very long time without slowing down. These are superfluids, liquids that act as if friction has quietly stepped out of the room. You don't have to sit up or think too hard for this. You can stay exactly as you are, resting where you are, and just let the images drift by. Imagine a small cup, not on your bedside table, but in a laboratory, cooled to temperatures very close to absolute zero. Inside is liquid helium. Helium is already a bit unusual. Even when you make it very cold, it refuses to become a solid at normal pressure. Where water would freeze into ice, helium stays liquid, as if it prefers to keep dancing. As experimenters cooled liquid helium further, past a certain temperature, about 2 degrees above absolute zero, they noticed something astonishing. The liquid changed character. Below this temperature, called the lambda point helium-4 becomes a superfluid And superfluid helium does things that look almost like magic if you don't know the physics behind it. One of the most famous images is this. Pour some superfluid helium into a shallow container. Instead of just sitting there, it can slowly creep up the walls, flow over the edge, and drip down the outside, as if gravity and common sense were gentle suggestions rather than strict rules. It's not that gravity is gone, it's that the liquid's ability to flow without resistance lets it respond to tiny forces that an ordinary liquid would ignore. You can picture it like this. An ordinary liquid is like a crowd trying to push through a narrow doorway, bumping shoulders and getting in each other's way. A superfluid is like a perfectly coordinated group moving through a maze, slipping through every opening without jamming. Another strange feature is that superfluid helium can flow through incredibly narrow pores, tiny channels that would completely block a normal liquid. The absence of viscosity lets it slide through gaps that would otherwise be impassable. If that sounds a bit unreal, that's okay. You don't have to picture every detail. Just hold on to the soft idea that this liquid acts as if it has no internal friction, no tendency to slow down once it's in motion. Under certain conditions, superfluids can form persistent currents, flows that go around and around a loop without gradually dying out the way a stirred cup of tea does. Imagine stirring your drink once and watching it spin, not for seconds, but for hours or longer, as if no energy were being lost. In the real world, practical imperfections and interactions eventually spoil the perfection. But compared to ordinary liquids, the difference is dramatic. What's going on underneath this behavior? Remember the Bose-Einstein condensate. Many particles sharing one quantum state, moving in a coordinated, wave-like way, rather than as a collection of independent marbles. Superfluid helium-4 can be understood, in a simplified way, as a kind of asterisk macroscopic quantum state, asterisk 2. Its atoms, which behave effectively as bosons, can fall into a coherent, ordered pattern at very low temperatures. The liquid's flow is then governed by these quantum rules. Instead of every atom making its own decisions, the superfluid behaves as if it is described by a single, smooth wave function, a mathematical object that encodes its quantum state. Changes to that wave function affect the entire liquid. You don't need the equations. You can think of the superfluid as a liquid that has become a choir instead of a crowd, its particles moving in harmony so that random, friction-like jostling is suppressed. There are also superfluids made from helium, 3 **, an isotope of helium with different quantum properties. To become superfluid, helium-3 atoms, which behave as fermions, first pair up in a way that turns them into effective bosons, a bit like electrons pairing up in superconductors. These pairs can then form a coherent state with remarkable properties. The details of helium-3 superfluidity are rich and subtle, involving intricate patterns of pairing and internal structure. For a sleepy science story, it's enough to know that even fermionic particles, if they pair correctly, can join this quiet dance of superfluidity. You might notice a theme here. Bose-Einstein condensates, superfluid helium, and, soon, superconductors all share a family resemblance. Many particles acting as a single, extended quantum state. When that happens, familiar limits like viscosity for liquids or resistance for currents can soften or disappear. In the lab, superfluids show other peculiar behaviors. There is something called the asterisk fountain effect ***. When part of a superfluid is warmed slightly, it can create a flow that pushes the liquid up through a narrow channel, as if forming a tiny fountain against gravity. This happens because the superfluid component responds to temperature differences in a way that ordinary fluids do not. In rotating containers, superfluids can't just spin in any arbitrary pattern. Instead, they form thin, quantized vortices, tiny whirlpools whose circulation is fixed by quantum rules. It's as if the fluid can only rotate in discrete steps, not continuously. Again, you don't need to file away the technicalities. You can imagine a bowl of superfluid spinning and forming a regular, almost crystalline arrangement of miniature tornadoes, too small to see with your eyes but too orderly to be random. All of this might sound far removed from your room right now, where the only fluids you're likely to see are water, tea, maybe juice, or milk, all obeying the usual rules. But that contrast is part of the beauty. Under everyday conditions, the quantum nature of matter is mostly hidden. Friction, randomness, and thermal noise dominate. At extremely low temperatures, in carefully prepared systems, that noise quiets down, and the underlying quantum order emerges in ways we can actually measure. Superfluids remind us that liquids are not just wet stuff that flows in one general way. They can adopt very different personalities depending on how their particles organize themselves. If you like metaphors, you can think of it like this. Ordinary liquids are like busy city streets, with cars starting and stopping, honking, jostling, losing energy at every turn. A superfluid is like an empty, perfectly smooth highway, with cars that never run out of fuel and never collide. Once they start moving, they just keep going, quietly and endlessly, unless something very specific gets in the way. You might also notice how these ideas sit alongside your own body's experience of stillness. As you lie there, breathing slowly, you may feel that parts of you are very still. Your hands resting, your legs supported, your head sinking into the pillow. And yet, inside you, blood is flowing, air is moving in and out of your lungs, countless molecules are in motion. Superfluids live in that paradox too. The appearance of perfect calm on one scale, and subtle, coordinated motion underneath. In the next stretch of our journey, we'll take this idea of flow without resistance and apply it to something else. Not a liquid flowing through a pipe, but asterisk, asterisk, electric current, asterisk, asterisk, flowing through a solid. Because just as superfluids can ignore viscosity, some materials, when cooled enough, can let electrical currents flow with asterisk, asterisk, zero resistance, asterisk, asterisk. They become superconductors, and they can do their own quiet magic tricks. For now, though, you can let superfluids be a soft, half-remembered dream, a liquid that refuses to slow down, climbing walls, slipping through tiny passages, forming quantum whirlpools you can't see. You don't have to sort every image into a neat box. You can just remember that, hidden beneath the ordinary behavior of fluids, there is a deeper, quantum story, one that only reveals itself when things are cooled almost to the edge of absolute zero. If your eyelids are heavy, you can simply rest with this thought. Somewhere, in a very cold lab, a tiny puddle of helium is quietly doing impossible things, flowing without friction, obeying rules that only show themselves when the world is almost perfectly still. And somewhere closer, your own thoughts are slowing down too, flowing more gently from one idea to the next. When you're ready, we'll move on to the next cousin in this family of quietly extraordinary states. Materials where electricity too learns how to glide without losing energy, turning wires into nearly perfect paths for current, in the same way superfluids are perfect paths for flow. Now that we've watched liquids learn how to flow without friction, let's let the same idea slip into something even more familiar: electricity. We're used to thinking of electric current as this invisible thing that moves through wires, making lights turn on, phones charge, fans spin. It just feels like a quiet background service, always there when you flip a switch. But underneath that everyday feeling, there's a tiny struggle going on. In an ordinary wire, electrons move through a lattice of atoms, like people trying to walk through a crowded hallway. They bump into things. Vibrating atoms, impurities, tiny defects. Every time they scatter, a little bit of electrical energy is turned into heat. That's why wires can warm up, why bulbs glow from resistance, why chargers get slightly warm in your hand. This tendency to resist the flow of current is what we call electrical resistance. It's the friction of the electronic world. Now, here's the part that quietly breaks that rule. There are materials which, when cooled enough, suddenly stop resisting. Their electrical resistance drops not just a little bit, but all the way to effectively zero. In that state, electrons can flow through them in a loop, round and round, without losing energy, for incredibly long times. These are superconductors, the electrical cousins of superfluids. You can imagine this chapter as shifting our focus from a flowing liquid in a lab to a loop of wire deep inside a cold, humming cryostat. You don't have to picture all the equipment. You can stay exactly where you are, lying down, breathing slowly, maybe feeling the weight of the blankets. We'll just let our thoughts wander over to this strange, quiet way that current can move. Think first of an ordinary wire. In your mind, zoom in until you see a line of atoms arranged in a repeating pattern, a crystal lattice. Electrons weave their way through this structure. They don't have one perfectly clear path. They interact with the atoms and with each other, and that makes them scatter. Now imagine slowly cooling this wire. As the temperature drops, the atoms in the lattice vibrate less. The hallway becomes a little calmer. The resistance goes down, not to zero, but lower. For many materials, that's the whole story. Cooler means lower resistance, but some always remains. But in certain metals and alloys, something remarkable happens at a specific temperature called the critical temperature, Cross that threshold, and it's as if a switch flips. Resistance doesn't just decrease smoothly, it collapses. The material suddenly becomes superconducting. You don't have to remember the precise numbers, just the feeling. Above this critical temperature, current is constantly struggling. Below it, it glides. How can that be? Deep down, superconductivity is another example of many particles moving in a coordinated, quantum way. Just as atoms in a Bose-Einstein condensate can share a single state, electrons in a superconductor stop acting like a disorganized crowd and start behaving in pairs, moving in harmony. In an ordinary metal, at higher temperatures, electrons are like people in that busy hallway, rushing, scattering, bouncing off obstacles. In a superconductor, many of them form pairs, known as Cooper pairs, named after the physicist Leon Cooper. These pairs aren't like little physical couples holding hands. They are a quantum partnership, spread out over distances much larger than an individual atom. When the material is cold enough, an enormous number of these pairs fall into the same collective state, a bit like what happens in a condensate. Instead of each pair making its own decisions, they move together, described by a single, large-scale wave. Because of this, scattering, the thing that normally causes resistance, no longer happens in the usual way. To disrupt this coherent state, you would have to break many of these pairs at once and disturb a whole pattern, which costs energy. At low enough temperatures, the random fluctuations that might do that simply don't have enough energy, so the pairs glide through the lattice without the usual losses. You don't need the equations for that. You can just imagine that the electrons have stopped acting like a lot of separate marbles and have become something more like a smooth river of charge, hard to disturb without a deliberate push. Superconductors also do another quiet trick. They expel magnetic fields from their interior when they transition into the superconducting state. This is called the Meissner effect. Imagine you cool down a piece of certain metal in the presence of a magnetic field. As it becomes superconducting, it rearranges its internal currents in such a way that the magnetic field is pushed out of its bulk, confined to a thin layer at the surface or repelled entirely, depending on the type of superconductor. Visually, you might picture this as a material that, once superconducting, prefers not to let magnetic lines pass through its heart. Instead, those lines bend around it, as if the material is saying, gently but firmly, no, thank you. From that simple fact, comes one of the most striking images in this part of physics: magnetic levitation. Place a small magnet above a properly cooled superconductor, and under the right conditions, the magnet can hover in mid-air, held up by the interplay between superconducting currents and the magnetic field. It can even be pinned in place, as if resting on invisible rails of field lines. You may have seen videos of this: a little disc floating over a track, gliding along quietly, no wheels, no bearings, just the silent handshake between superconductivity and magnetism. Again, it looks like magic, but underneath, it's a system relaxing into a quantum state where the energy is minimized by expelling or shaping the magnetic field in specific ways. The magnet finds a position where forces balance, and there it rests, weight supported by invisible structures of field and current. All of this happens at low temperatures because thermal agitation, the random jostling we call heat, tends to break apart the fragile quantum order. Heat is like noise. Superconductivity is like a delicate song. Turn the noise up too high, and the song can't be heard. The first superconductors discovered in the early 20th century had very low critical temperatures, just a few degrees above absolute zero. That meant they needed to be cooled with liquid helium, which is expensive and technically demanding. Later, researchers discovered high-temperature superconductors, still very cold by everyday standards, but with critical temperatures high enough that they can be cooled using liquid nitrogen, which is much cheaper and easier to handle. These materials are often complex ceramics rather than simple metals. Even today, the exact mechanisms behind some of these high-temperature superconductors are not fully understood. They are part of ongoing research, a reminder that even within this hidden state of matter, there are still mysteries quietly waiting. If that feels like a lot, that's all right. You don't need to catalog the types of superconductors or memorize their temperatures. You can just keep the soft idea that, for some materials, cooling unlocks a state where electrical current can move without resistance and magnetic fields behave in unusual ways. This ability has practical uses. Strong, stable superconducting magnets are used in MRI machines in hospitals, where they create precise magnetic fields for imaging the inside of the human body. These magnets can run for long periods because the currents inside them don't fade away from resistance. There are experimental power cables made from superconducting materials designed to carry large currents over distance with very little loss, avoiding the energy wasted in traditional wires. Some transportation concepts, like certain designs for magnetic levitation trains, lean on superconducting ideas, using levitation and guidance from magnetic interactions to move with very low friction. There are also sensitive instruments called SQUIDs, superconducting quantum interference devices, that can detect incredibly tiny magnetic fields, used in research and specialized measurements. You don't need to know each device by name. Just picture a family of quiet technologies that rely on this peculiar, cooperative state of electrons to do things that ordinary materials cannot. If all the details blur together into one soft impression, currents that don't fade, magnets that float, wires that don't heat up, that's more than enough for a sleepy journey. There's also a deeper, philosophical whisper here. Superconductors, like superfluids and condensates, remind us that the behavior of matter is not fixed once and for all. The same atoms, under different conditions, can organize themselves into entirely different patterns. At room temperature, a piece of metal might be just a good conductor with some resistance. Cooled below its critical temperature, the same piece becomes something else, a superconducting state, with new rules, new possibilities. It's as if the material has multiple personalities, and temperature is the key that unlocks which one you see. You might think of your own life in a gentle parallel. The same person can be quiet or energetic, focused or dreamy, depending on context. The state you're in changes how your abilities show up without changing who you are at the core. Matter does something similar, but in a much more fundamental way. If your eyelids are heavy now, that's okay. You don't need to keep track of every analogy and every term. You can let superconductivity be, in your mind, a peaceful picture, a loop of wire carrying current endlessly, no heat, no loss, just a quiet, persistent flow. Somewhere, deep in a cold lab, such loops exist, currents that were started long ago and still continue, drifting round and round a ring of superconducting material, like a thought that never quite fades. In our journey through the hidden states of matter, we've now seen both extremes of calm cooperation: superfluids that flow without friction, and superconductors where electrons glide without resistance. We've seen matter cooled almost to stillness, revealing its quantum order. In a little while, we'll take a very different turn. We'll move from the ultra-cold back to the ultra-hot, to a state where the building blocks inside, protons and neutrons, quarks and gluons, are set free in a short-lived, fiery soup. A state that existed in the first moments after the Big Bang, and that we now recreate briefly in powerful particle colliders. But for now, you don't have to rush ahead. You can stay here, in this quiet room of the story, resting with the idea that even something as simple as a wire can, under the right conditions, become a place where current flows perfectly, endlessly, without struggle. If your mind wants to drift away from the physics and back to your breathing, to the feel of the bed or the seat beneath you, you can let it. Somewhere far away, magnets are floating, currents are circling, and quantum pairs of electrons are moving together in silent agreement. And here you are, warm and safe, listening to the gentle tale of how matter, when cooled enough, learns to cooperate in ways we're still learning to understand. We've spent some time in the quiet, ultra-cold corners of the universe, where atoms huddle into single waves and liquids learn how to flow without friction. Now, very gently, we're going to do the opposite. Not in your room, of course. You can stay exactly where you are, warm, safe, breathing slowly. But in your imagination, we're about to turn the temperature dial not just up, but almost all the way to the beginning of everything. Now here's the part where things get stranger again, but we'll move through it slowly. Imagine rewinding the universe. Galaxies drift back together. Stars unform. Planets, including this one, dissolve into clouds of hot gas. Keep going back, past any familiar landmark, until the entire universe is compressed into something far smaller, far denser, far hotter than anything we can truly picture. In those first tiny fractions of a second after the Big Bang, the universe wasn't made of atoms at all. It was filled with a kind of incredibly hot, incredibly dense soup of more fundamental ingredients, quarks and gluons, along with other particles and their antiparticles. This state is called a asterisk quark gluon plasma asterisk. To get a feeling for it, think of the protons and neutrons inside the atoms around you. Those familiar particles are not fundamental. They're made of quarks, held together by gluons, the carriers of the strong nuclear force. In ordinary matter, quarks are confined. They're locked inside protons and neutrons, like beads sealed inside tiny capsules. You never see a free quark wandering around on its own for long. It's always bound up in a larger particle. But in a quark-gluon plasma, the temperature and density are so extreme that those capsules melt. Quarks and gluons are no longer confined into individual protons and neutrons. Instead, they move in a hot, dense, strongly interacting fluid, a kind of primordial soup where the usual boundaries between particles are blurred. You can imagine it as taking all the marbles in a bag, crushing the bag, and heating everything until the marbles themselves dissolve into a glowing fog of their building blocks. According to our best cosmological models, the universe spent a short, early phase in this quark-gluon plasma state, during what's sometimes called the **quark epoch**, from roughly 10 to the power of -12 to 10 to the power of -6 seconds after the Big Bang, before cooling enough for quarks to lock into protons and neutrons. Those numbers are almost impossible to grasp emotionally. The age we're talking about is so early that if the universe's entire history was stretched across a year, this would be less than the first blink of the very first midnight. But you don't need to feel the numbers. You can simply picture an unimaginably hot fog of quarks and gluons filling all of space before anything like stable atoms or stars or galaxies existed. For a long time, this sounded like a story we could only tell about the past. But then physicists asked a bold, slightly wild-sounding question. What if we could make a tiny, short-lived version of this early universe state here on Earth? Not a universe, of course, just a microscopic drop. A little bang instead of a big bang. To do this, they built giant machines, particle accelerators, where they can take heavy atomic nuclei, like gold or lead, strip off their electrons, and then smash those bare nuclei into each other at nearly the speed of light. When two of these heavy ions collide head-on at such extreme energies, the matter in the overlap region is compressed and heated to incredible temperatures, trillions of degrees, for a fleeting moment. In that instant, the protons and neutrons inside are believed to melt into a tiny droplet of quark-gluon plasma, which then rapidly expands and cools, turning back into ordinary particles that fly out toward detectors. We never see the quark-gluon plasma directly. What we see is the spray of particles that comes out after it cools and freezes out. By measuring those particles carefully, their energies, directions, types, scientists reconstruct what must have been happening in that tiny fireball just before it faded. At first, many theorists expected this plasma to behave like a thin, weakly interacting gas of quarks and gluons. But the experiments at places like RHIC in the United States and the Large Hadron Collider in Europe showed something surprising. The quark-gluon plasma created in these collisions behaves less like a simple gas and more like an almost perfect liquid, a strongly coupled fluid with extremely low viscosity, meaning it flows with very little internal friction. You can think of that in contrast to, say, honey, which has high viscosity and resists flowing, or even water, which has some viscosity but flows easily. The quark-gluon plasma seems to be closer to a theoretical limit, where a fluid flows as smoothly as the laws of quantum physics allow. That's a quiet twist. The hottest matter we know how to make turns out to behave like one of the smoothest liquids we've ever seen. How do we know it behaves like a liquid? One clue comes from the way this tiny droplet expands. When the colliding nuclei don't hit perfectly head-on but a bit off-center, the overlapping region is shaped more like an almond than a circle. If the matter inside were just a gas with particles flying independently, the final spray of particles would more or less smear that shape out. But what experiments see is a pattern of flow. More particles emerge along the short axis of that almond shape than along the long axis, as if the droplet expanded collectively, like a fluid responding to pressure differences. This elliptic flow pattern matches what hydrodynamic models, the same kind of equations used to describe ordinary fluids, predict for a nearly perfect liquid. You don't need to follow every detail of that. You can simply hold onto a gentle idea. When we smash heavy ions together at extreme energies, the matter inside doesn't behave like a messy explosion of individual particles. but more like a tiny, coordinated droplet of fluid. It forms, flows, and then freezes into a spray of particles, all in less time than it takes light to cross a nucleus. If you like images, you might picture it like this. In a gigantic ring buried underground, long streams of ions speed around in opposite directions, guided by powerful magnets. When they finally collide, deep within a detector full of layers of sensors, a tiny region of space is briefly heated to temperatures higher than in the core of any star. Inside that speck, quarks and gluons swirl together in a brief, liquid-like state, then cool and re-solidify into particles that race outward, leaving traces like sparkles in carefully timed electronics. All of this happens again and again, millions of times, building up a statistical picture of this strange, hot state. From a sleepy distance, you can think of it as humanity's way of recreating a drop of the early universe in a controlled, repeatable way, a tiny echo of conditions that once filled all of space. So we now have, in our tour of hidden states, another corner, at the cold extreme, where motion nearly stops, matter can form calm, ordered quantum states. Bose Einstein condensates, superfluids, superconductors. At the hot extreme, where motion is pushed to extraordinary energies, matter can also change its identity. Protons and neutrons lose their boundaries. Quarks and gluons roam more freely, and this quark-gluon plasma flows like a nearly perfect fluid. In between, at ordinary temperatures, we get the familiar world: solids, liquids, gases, plasmas in stars, and lightning, the phase changes we see in our kitchen and our weather. You don't have to remember the names Rick or LHC, or how many trillions of degrees we're talking about. You can let all of that soften into a simple thought. Matter has another hidden state, one that appears when you turn the temperature up far beyond anything we experience, back toward the conditions at the dawn of the universe. In that state, the building blocks that usually live inside protons and neutrons move through a hot, dense, fluid-like medium, leaving behind subtle clues that we read in detectors. There is a quiet symmetry between this and the ultra-cold states we visited earlier. At one end of the thermometer, cooling brings order. Particles lock into collective quantum patterns, cooperating in calm, coordinated waves. At the other end, heating to extremes also brings a kind of collective behavior. Quarks and gluons, liberated from their usual confinement, form a strongly interacting liquid that flows together with surprising smoothness. Both extremes reveal that, beneath the everyday surface, matter is capable of patterns far beyond the simple three-state picture we learn in school. If your mind feels full, you can let most of this story drift away. Maybe you keep only one image, a tiny, short-lived droplet of the early universe, recreated inside a machine on Earth, flowing like a perfect liquid for the briefest instant before freezing into particles that whisper its properties to careful observers. Somewhere, deep in those accelerators, that process is happening over and over again while you lie here, breathing slowly, wrapped in familiar matter at familiar temperatures. In a moment, we'll leave the extremes and take a gentler step back to look at some of the other exotic phases that sit between these famous examples: liquid crystals, topological phases, and other quiet curiosities that show how matter can arrange itself in ways that are neither fully solid nor fully fluid in the usual sense. But you don't need to hurry with us. For now, you can rest with this old new thought. The universe you're in today, with stars and planets and pillows and mugs, is, in some sense, the cooled, settled descendant of a time when everything was a quark-gluon plasma. The hidden state we recreate in colliders is not science fiction. It's a memory, a tiny echo of the way everything once was, before matter learned to take on all the quieter forms that now fill your room. Now that we've visited both extremes, the ultra-cold quantum puddles and the ultra-hot primordial soup, let's do something gentler. Let's wander through a quiet gallery of in-between states, not as famous as plasmas or condensates, but tucked all over your everyday life and in the notebooks of curious physicists. Now here's the part that quietly shifts the rules again. We're going to meet states of matter that are not quite solid, not quite liquid, not quite conductor, not quite insulator, but something in between. Not broken rules, exactly just different, more intricate patterns. You don't have to sit up or concentrate hard. You can stay exactly as you are, maybe feeling the softness of your pillow, the familiar weight of your blanket, the slow rhythm of your breathing. Just let these examples drift past like exhibits in a museum you're strolling through half awake. Imagine, first, your phone or a TV screen in a dim room. When the screen is on, it glows with tiny pixels of color, changing fast enough to show moving images. Inside many of those displays is a state of matter you don't see directly, but you've used thousands of times. A ***, liquid crystal, ***. The name itself sounds like a contradiction. Liquids flow. Crystals are rigid, ordered, and solid. But liquid crystals are, in a sense, both. Imagine a row of tiny matchsticks, all lined up in roughly the same direction, but floating in a liquid. They can move around, slide past each other, like a liquid, yet they also maintain some overall alignment, like a crystal that has a preferred direction. That's the essence of many liquid crystal phases. Molecules that can flow like a liquid, but keep some directional order, pointing more or less the same way. When we place them between thin glass plates and apply electric fields, we can nudge that orientation, twist it, straighten it, reorient it. By controlling how the liquid crystal twists or aligns, we change how it interacts with light passing through, and that's one of the key tricks behind LCD screens. You can think of each pixel as a tiny adjustable window whose blinds are made of liquid crystal molecules. By changing the electric field, we tilt those blinds and decide how much light gets through and what color filters it passes. You don't need to remember the specific phases or names. You can just hold the soft idea that there are states of matter that sit between familiar categories, not fully rigid, not fully disordered, and that your everyday screens quietly rely on this in-between behavior. If that sounds odd, don't worry. You've already lived with liquid crystals for years. They've been shining movies and messages into your eyes without demanding that you learn their name. Now, let's drift to something more abstract and quietly profound. ***, topological phases, *** of matter. This is one of those ideas that, if you try to grab it too tightly, slips away. So we won't grab, we'll just lightly touch it. In ordinary phases like solid, liquid, or gas, we often classify them by symmetry and order, where the atoms are, how they repeat, how they move. Topological phases, on the other hand, are organized by something deeper, global properties that stay the same even if you stretch or gently deform the material, as long as you don't tear it or change it too violently. A common analogy is shape. A coffee mug and a donut, if made from very flexible clay, can be smoothly deformed into each other without cutting or gluing. Each has one hole. A ball, by contrast, has no holes. From a topological point of view, the mug and donut belong to one class, the ball to another. In some materials, the way electrons can move and arrange themselves is determined by similar topological classes. Two materials may look quite different in microscopic detail, but share the same topological features, and thus have similar robust properties, especially at their edges or surfaces. One famous example is a asterisk topological insulator asterisk. In the bulk, deep inside, the material behaves like an insulator. Electrons don't move freely, but at the surface, it conducts electricity in special, protected ways. Those surface states are robust. They can't easily be removed by small impurities or deformations. They're tied to the material's topological character, the way a donut's hole is tied to its overall shape. You don't have to compute anything here. You can simply imagine a material whose interior is quiet and stubborn, refusing to conduct, while its surface is lively, electrons gliding around the edges, protected by deep mathematical rules. It's a bit like a very calm lake whose shoreline is secretly buzzing with activity. These topological phases show up in phenomena like the asterisk quantum Hall effect asterisk, where electrons confined to 2 dimensions and subjected to strong magnetic fields move in precise, quantized patterns. In those systems, the conductance, how easily current flows, takes on certain fixed values that are amazingly stable, even when the material is imperfect. From a sleepy distance, you can think of it this way. Some phases of matter are not just about where atoms sit, but about how entire patterns of motion and wave-like behavior wrap around in space, forming structures that can't be undone without a major change. We can step even more lightly across a few other exotic states. There are systems where electrons pair not for superconductivity, but in different ways. Systems where electron-hole pairs called excitons can condense into shared quantum states, forming asterisk, exciton condensates, asterisk. There are gases of atoms excited to very high energy levels, asterisk, Rydberg atoms, asterisk, that can interact strongly and form unusual, extended patterns because their electron clouds are huge compared to ordinary atoms. Some materials exhibit asterisk charge density waves, asterisk, where the electron density in a crystal undulates in a regular pattern, like a standing wave frozen into the arrangement of charges. Others show asterisk, spin liquids, asterisk, where the magnetic moments, spins of electrons, never settle into a rigid pattern, but continue to fluctuate in a correlated, entangled way even at very low temperatures. You absolutely do not need to remember any of these names. They can pass by like constellations in a sky you're glancing at through half-closed eyes. The message is quieter and simpler. Matter is not limited to 3 or 4 or even 5 states. The number of possible phases, distinct ways particles can organize themselves is vast. Each one is like a different style of conversation between particles, sometimes loud and disordered, sometimes quiet and ordered, sometimes rigid, sometimes flowing, sometimes sensitive to shape and topology rather than local details. Scientists keep discovering new phases, especially in carefully designed, low-dimensional systems, thin films, 2-dimensional materials, ultra-cold gases, layered crystals. Each new phase is like adding another chapter to an ever-growing atlas of how matter can behave. You might imagine a shelf of books titled States of Matter, and the first few volumes are solids, liquids, gases, plasmas. Then someone opens a hidden cupboard and you see more volumes. Bose-Einstein condensates, superfluids, superconductors, quark-gluon plasmas. And behind that, another shelf appears, filled with liquid crystals, topological insulators, quantum spin liquids, exciton condensates, and room for many more titles yet unwritten. From your perspective, lying in bed or resting on a couch, this might feel very far away from your daily life. But traces of these exotic phases are already woven into your routine. The screen glowing beside you owes part of its function to liquid crystals or related technologies. Certain advanced materials in electronics, sensors, and experimental devices rely on subtle quantum and topological behaviors. Even if you never see the equations, you live in a world that quietly depends on matter's more unusual moods. If this feels overwhelming, let it soften. You don't have to hold all the details at once. You can simply remember that matter has many more ways to be than the three you learned as a child. Some of those ways are gently in between, like liquid crystals. Some are protected by deep, shape-like mathematical properties, like topological phases. Others are still being mapped out. There is also a comforting thought in there. We don't know all the phases yet. Just as we once thought there were only solid, liquid, and gas, and later added plasma and more, it's likely that the story is still incomplete. New states, new patterns, may be waiting in corners of temperature, pressure, and structure we haven't fully explored. That means the universe still has surprises, but they're not jump-scare surprises. They're slow, patient discoveries, new ways that familiar particles can arrange themselves, new chapters in a story that keeps unfolding. You might think of your own life again. Softly, how many states have you been in? Childhood, adolescence, adulthood, times of energy, times of rest. Same person, different patterns, different ways of being. Matter does its own version of that, but with atoms and fields instead of thoughts and feelings. As your eyes grow heavier, you can let this chapter fade into a simple, gentle idea. The world around you is made of matter that can take on many, many hidden forms. Some of those forms light up your screens. Some guide electrons along special paths. Some exist only in labs, at extremes of cold or heat. Some may not have been discovered yet. And all the while, your pillow is a solid, your drink was a liquid, the air is a gas, and somewhere far away, stars blaze as plasmas. On top of that, in tiny pockets and carefully crafted materials, matter is also quietly being a liquid crystal, a topological insulator, a condensate, or something we haven't named yet. You don't need to sort them all out. You can just rest with the knowledge that the universe is richer, more varied, and more softly strange than the simple diagrams in a schoolbook ever managed to show. In a moment, we'll step back from this gallery and reflect on what all of these hidden states tell us about reality itself, about patterns, uncertainty, and the way we live with not knowing everything. But for now, if you'd like, you can simply breathe in and out, and let the idea of many possible states settle over you like a calm, gentle blanket. Now that we've wandered through so many strange and hidden states of matter, there's a quiet question waiting in the background. How do we even know all of this? How do scientists discover a new state of matter, or decide that something is not just a weird version of a solid, but a truly different phase, deserving its own name and place in the story? This chapter is a little like stepping behind the scenes of a theater. We've watched the performance condensates, superfluids, superconductors, plasmas, exotic phases. Now we're going to peek at the lighting rigs, the props, the notes on the director's clipboard. Don't worry, we'll move slowly. You don't need to remember what any particular machine is called. You can stay exactly where you are, lying in bed, on a couch, maybe with your eyes half closed, and just let this gentle, how they know, chapter drift over you. You might remember, back in school, seeing a simple picture, a diagram with solid, liquid, and gas, written in boxes, with arrows between them for melting, freezing, boiling, condensing. Scientists use something a bit more grown up, but it carries the same spirit. Asterisk, asterisk, phase diagrams, asterisk, asterisk. Imagine a map. Instead of north-south and east-west, the axes are asterisk, asterisk, temperature, asterisk, asterisk, and asterisk, asterisk, pressure, asterisk, asterisk. At low temperatures and moderate pressures, you might see a region labeled solid. As you move horizontally to higher temperatures, you cross a boundary into liquid. Move further, and you cross into gas. Each region is a phase. Each boundary line is a place where the substance changes its state. You can picture this as a landscape, valleys and hills painted with labels. Over here, ice. Over there, liquid water. Up above, steam. At certain points, the boundary lines meet a ****, triple point ****, where solid, liquid, and gas can coexist in delicate balance. For a simple substance like water, that's already quite a story. But scientists don't stop at water, and they don't stop at 3 phases. They make phase diagrams for many different materials, adding more axes when needed. Magnetic field, composition, even quantum parameters for more exotic systems. So, how do they draw these maps? They don't start with the diagram. They start with *** experiments, ***. You might imagine a carefully sealed chamber holding a sample of some material, maybe a gas, maybe a crystal, maybe a weird alloy. They can adjust the temperature, cool it down, heat it up. They can change the pressure, squeeze it, release it. They can apply magnetic fields, electric fields, mechanical strain, and as they move through these conditions, they watch. Sometimes they literally watch with their eyes. Does it melt? Does it crack? Does it flow? More often, they watch with instruments, measuring *** electrical resistance, ***, heat capacity, ***, magnetization, optical properties, or the way the material scatters X-rays and neutrons. If, as they slowly change temperature, something in the material's behavior changes sharply, its resistance suddenly drops, its heat capacity spikes, its structure rearranges, that's a clue. A *** phase transition *** may be happening. You can think of it like listening to someone's voice as they walk through different rooms. In one room, their voice echoes in a certain way. In the next, it sounds different. From those changes, you infer that the walls, the shape, the acoustics have changed. In the same way, changes in how a material responds to probes tell scientists that its internal architecture has changed. Sometimes the transition is dramatic and obvious. Ice melting into water, a metal turning superconducting with a sudden drop to 0 resistance. Sometimes it's subtle, a new pattern in the spins of electrons, a small kink in a graph that hints at a hidden reorganization. Bit by bit, measurement by measurement, they plot these changes on a graph. At this temperature and pressure, the material behaves like this. At that point, it behaves like that. Connect the dots, and you get phase boundaries. Over time, a blank map starts to fill in. This region is phase A. That region is phase B. Over here, something new happens that doesn't fit either description. Now here's the part that quietly brings in curiosity again. Sometimes, the measurements don't fit any known phase at all. Maybe the material conducts electricity in a strange way. Maybe its magnetic moments never settle, even at very low temperatures. Maybe its properties are robust against impurities, in a way that hints at topology, not just local structure. Those puzzles become invitations. Is this a new state of matter? Are we seeing a known phase in a new regime, or something genuinely different? To answer those questions, scientists combine experiments with *** theory, ***. Theorists build models, simplified versions of the material and its interactions, and use mathematics and simulations to predict what phases might exist under different conditions. They might say, if electrons in this material interact in this particular way, we expect a phase that behaves like a topological insulator. Or, if atoms in this gas are cooled below this temperature, they should form a condensate. Experimentalists then go hunting for those predicted phases, tuning their equipment to reach the right regimes. Other times, the experiment comes first. An unexpected anomaly appears in the data, and theorists scramble to explain it, proposing new phases and mechanisms that could account for the strange behavior. It's a quiet loop of conversation between theory and experiment, like two friends passing notes back and forth in a very complicated classroom. You can picture an experimentalist gently turning the temperature knob on a cryostat, a device that cools things to extremely low temperatures, watching the readout of resistance, magnetization, or some other property. At a particular temperature, the graph suddenly changes slope, or drops, or spikes. They write it down. They repeat the measurement. They try different pressures, different magnetic fields. They see where that change happens and where it doesn't. Slowly, the data traces out a line in the temperature-pressure plane. Here is where the phase transition occurs. What about the more extreme states we talked about? For Bose, Einstein, condensates ***. Scientists map out where the condensate appears by measuring the momentum distribution of atoms in an ultra-cold gas. Above a certain temperature, the cloud behaves like a normal gas. Below it, a sharp peak appears, signaling that many atoms share the same quantum state. For superconductors they draw a phase diagram showing regions where the material is normal and where it is superconducting as a function of temperature, magnetic field, and sometimes doping, how many extra electrons or holes are added. The boundary between those regions is the superconducting phase boundary. Cross it, and the material quietly shifts from resistive to resistance-free. For quark, gluon, plasmas, the phase diagram is even more abstract. Temperature versus something called baryon, chemical potential, a measure loosely related to how much matter versus antimatter is present. In colliders, scientists change collision energies and the types of ions they smash together, then read off signs of collective behavior in the particle sprays. By comparing these patterns to models of how a quark-gluon plasma should evolve, they infer where, in that abstract phase diagram, the collision might be landing. You don't need to follow every technical step. You can just keep this gentle picture. Scientists push matter into different conditions: hotter, colder, denser, more rarefied, under fields and pressures, and listen, to how it responds. Every response is a hint about its internal state. Sharp changes signal boundaries. Unusual patterns signal something new. There's another layer, too, the idea of a critical point, In some systems, there are special points in the phase diagram where the distinction between phases becomes subtle. For water, for example, above a certain critical temperature and pressure, the line between liquid and gas disappears. Beyond that, there's just a supercritical fluid, not quite liquid, not quite gas, but something in between, where you can move from more liquid-like to more gas-like without crossing a sharp boundary. Near critical points, fluctuations grow large. The material becomes especially sensitive, with regions of one phase blooming inside the other in complex patterns. Physicists use ideas from critical phenomena and renormalization to describe these behaviors, discovering that very different materials can show similar patterns near their critical points. From a sleepy distance, you might just imagine parts of the phase diagram where the map's borders blur and the line between phases becomes hazy. Even there, There's structure, but it is subtle and rich. All of this mapping takes time, decades, sometimes. Different labs cross-check each other's results. New techniques, better lasers, colder refrigerators, more sensitive detectors open up new corners of the diagram that were previously unreachable. And every now and then, a new region is discovered. A pocket where behavior is so different from anything seen before that people say, cautiously at first, we might be looking at a new phase of matter. There's something quietly comforting about this process. It's not one dramatic moment of revelation. It's many small steps. Data points, graphs, careful analysis. The map of matter's possible states is not written by a single hand, but by thousands of minds over many years, each adding tiny details, shading in new regions, correcting old boundaries. You can think of scientists as patient cartographers of reality's possibilities, charting where solids become liquids, where liquids become gases, where familiar behavior gives way to condensates, superfluids, superconductors, plasmas, topological phases, and more. And just like any map, it is always incomplete. There are likely whole regions we haven't reached yet, combinations of temperature, pressure, dimensionality, and interaction strength that no experiment has fully explored. Some may be impossible to reach in practice, living only in theory. Others may be waiting quietly in materials we already have, showing their unusual behavior only under very specific conditions. If your mind feels a little full, you can let most of that fade. You don't have to hold on to all the names or diagrams. You can just remember this soft idea. We discover hidden states of matter by gently pushing materials into new conditions and listening carefully to how they change. We draw maps, phase diagrams, to mark where those changes happen. We use theory and experiment together to understand what those maps are telling us. And just as your life has its own internal map, different moods, different phases, you move through with time and context, the universe has a vast, intricate map of how its particles can arrange themselves. We have explored only part of it. In the next chapter, we'll step back from the details, the diagrams, the experiments, the lab equipment, and look at what all of this tells us about reality itself, about patterns and uncertainty, about living with questions we can't fully answer, about how it can be strangely comforting to know that there are more phases to discover, more chapters to read in the book of matter. For now, though, you can rest. You can picture a quiet lab somewhere, a sample gently cooled or heated, a graph slowly tracing lines on a screen, and someone watching, patient and curious, adding one more small dot to the map of what matter can be. While they do that, you are here, breathing, supported by familiar solids, surrounded by familiar gases, with the hidden complexity of all these phases tucked softly into the world around you. Now that we've walked through so many hidden states of matter, from glowing plasmas to whispering condensates, from frictionless fluids to perfect currents and strange in-between phases, there's a soft, lingering question in the air. What does all of this times mean, asterisk, for how we see reality? Not in a grand, heavy way, more like a quiet thought you have staring out of a train window at night. Now, here's the part where things don't really get stranger. They just get more reflective. You don't have to understand any new physics here. This chapter is more about feelings than formulas. You can think of it as a slow, sleepy walk back through everything we've seen, looking at it from just a little farther away. You can stay exactly as you are. If you're lying in bed, feel the weight of the blanket over you. If you're sitting or half curled on a couch, feel the support under your body, the way your breath moves your chest, in and out, in and out. Somewhere far away, the universe is busy being complicated. Here, you get to just listen and drift. We started with the basic picture from school. Asterisk, asterisk, solid, liquid, gas, asterisk, asterisk. Simple, satisfying, easy to draw on the board. A mug, a drink, steam. But as we looked closer, that neat picture began to loosen. Solids, liquids, and gases weren't just labels. They were asterisk, asterisk, patterns of motion, asterisk, asterisk. Particles packed tightly and jiggling in place, sliding past each other or flying freely through space. Already, reality was telling us something. It isn't made of rigid categories handed down from the sky. It's made of asterisk, asterisk patterns, asterisk, asterisk ways things can arrange and move and respond. Change the pattern, and you've changed the state. Even if the ingredients are the same. The same water can be ice, liquid, or vapor. The same atoms in a metal can form an ordinary conductor, or, under the right conditions, a superconductor. The same helium can be a normal liquid or a superfluid that flows without friction. It's a bit like you. Same person. Different states. Calm, stressed, playful, tired, focused. Your ingredients, your memories, your body, your basic personality don't vanish. They just arrange themselves differently in different situations. Reality does that too. On a much deeper level, then we saw that when you push matter to asterisk, asterisk, extremes, asterisk, asterisk, the patterns it can adopt become even more surprising. At high energies, gas becomes asterisk, asterisk, plasma, asterisk, asterisk. Atoms shred into ions and electrons, and the universe glows in lightning and stars. At ultra-low temperatures, atoms fall into shared quantum states, asterisk, asterisk. Bose Einstein, condensates, asterisk, 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 asterisk. Superfluids, asterisk, 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 asterisk. Superconductors, asterisk, asterisk, where individuality fades and collective behavior appears. At ultra-high energies again, protons and neutrons melt into asterisk, asterisk, quark, gluon, plasma, asterisk, asterisk, a state that once filled the young universe and now exists, briefly, in particle colliders. Between all that, we wandered through asterisk, asterisk, liquid crystals, asterisk, 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 topological insulators, asterisk, 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 spin liquids, asterisk, asterisk, and other quiet curiosities, each with its own subtle way of organizing matter. There's a soft lesson hidden in that long list. Reality is not just stuff plus temperature. It's asterisk, asterisk, possibility space, asterisk, asterisk, a library of patterns waiting to emerge when conditions are right. Most of the time, we only see a few chapters of that library, the common states that show up in our daily lives. But the shelves are much, much longer than they first appear. You might wonder, in a gentle, late-night way, what does that say about reality itself? About what's real and what's just? How we're looking at it? Physics doesn't give final, poetic answers, but it does whisper a few hints. One hint is that asterisk, asterisk, things are often less important than the relationships between them, asterisk, asterisk. A solid is not just a collection of atoms, it's a pattern of how those atoms are arranged and how they interact. A superconducting state is not just electrons in a material, it's how those electrons move together. A topological phase isn't defined by one particular atom, but by how the whole system wraps around certain mathematical rules. Reality, it seems, cares a lot about asterisk, asterisk, structure, asterisk, 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 symmetry, asterisk, asterisk, and asterisk, asterisk, pattern, asterisk, asterisk. The state of matter is not just what it is made of, but how its parts cooperate. You can see a gentle parallel in human life. A family, a group of friends, a community. None of these are defined just by who is present. They're defined by asterisk, asterisk, how asterisk, asterisk people relate to each other, how they communicate, how they support or conflict, the pattern of connection, change the pattern, and the state of the group changes, even if the people are the same. Matter is doing its own version of that. Another quiet hint is about uncertainty. In the quantum world, particles are not little billiard balls with perfectly sharp positions and speeds. They are described by wave functions, probabilities, and possibilities. At normal temperatures in everyday life, that quantum fuzziness gets washed out by chaos. Everything jiggles and collides so much that the fine details blur away. But in certain hidden states, condensates, superfluids, superconductors, that quantum structure becomes visible on a large scale. It stops being a tiny footnote and becomes the headline. This tells us something gentle but profound. Uncertainty isn't just a mistake in our measurements. It's built into the fabric of the world, and under the right conditions, it shapes entire phases of matter. And yet, we still live in a universe that is, on the human scale, stable enough to have beds, cups, trees, cities, and you listening to this. So there's a balance. At one end, precise predictability fails. Quantum probabilities and phase diagrams take over. At the other end, the patterns are so robust that we can trust our chair not to dissolve under us. We live in between, in a world where mystery and reliability coexist. You don't need to fully understand that. You can just let it be a soothing thought. It's okay that not everything is certain. Reality itself is comfortable with a mix of clarity and ambiguity. There's also a comforting idea in how limited our early picture was, and how normal that is. For a long time, solid, liquid, gas seemed like the full story. Then plasma joined the list. Then condensates. Then all the other phases. Each time, the universe didn't change. Our map changed. We realized we'd been living in a much bigger house than we thought, with doors we hadn't opened and rooms we'd never visited. That's how science often works. We build a simple picture that works well enough. Then we push a bit further, colder, hotter, denser, thinner, stronger fields, lower dimensions, and that picture cracks, revealing something deeper. There is a gentle lesson there about knowledge in general, and even about your own life. It's okay if your current map of something isn't complete. It's allowed to be a draft. In fact, it has times to be a draft, because the world and you are always slightly more complicated than any neat story can capture. As you grow, you discover new phases in yourself, new capacities, new reactions, new ways of thinking. At one age, you might think you're simply shy, or confident, or not good at this or that. Later, under different conditions, you might discover that those labels were only part of the story, that there were hidden states of times that hadn't had the right conditions to appear. Just as matter needs the right temperature, pressure, or environment to show a new state, you sometimes need the right context, the right people, the right time for a new version of yourself to emerge. That's not a failure. It's how rich systems behave. There's one more whisper in all of this, about living with not knowing . If we listed every state of matter we know today, we'd still be missing some. New phases are still being discovered in laboratories and in astrophysical observations. Even for some of the phases we times know, like high-temperature superconductors, our understanding is still incomplete. We have pieces of the puzzle, but not the full picture. And that's okay. Science is not a finished book handed down from nowhere. It's an ongoing conversation with reality, where each generation adds more details, corrects some mistakes, and opens new questions. In your own life, you might feel a pressure to figure everything out. Who you are, what you want, how to handle every situation, what the future will look like. But the story of hidden states of matter suggests a softer alternative. It's normal for deep systems like the universe, and like you, to be only partially understood at any moment. You can know enough to move forward, to live, to choose. And it's also okay that there are regions of the phase diagram of your life you haven't charted yet. Uncertainty is not just something to fix. It can also be a space where new possibilities live. If your eyes are heavy now, you don't need to take anything more from this chapter than a couple of gentle thoughts. 1. Reality is made not just of things, but of patterns, ways those things arrange and move and relate. States of matter are different patterns written with the same particles. 2. Our knowledge is always a map, not the territory. As we explore new conditions, new states appear. The universe turns out to be larger, richer, and more quietly surprising than we first thought. 3. It's okay, deeply okay, to live with some mystery. To know that your understanding, like a phase diagram, is incomplete. And that's part of what makes the journey interesting. You don't have to solve reality before you fall asleep. You don't have to neatly file every state, every question, every feeling. You can just lie there, noticing the simple facts. There is a solid supporting your body. There is a gas filling your lungs. There are liquids flowing inside you. Far above, there are plasmas shining as stars. In hidden corners of labs and in the hearts of colliders, there are condensates, superfluids, superconductors, quark-gluon droplets, liquid crystals, topological phases. A whole secret life of matter is going on, whether you think about it or not. And here you are, one small, conscious patch of the universe, listening to its story and, for a little while, letting that story gently carry you towards sleep. In the next and final chapter, we'll gather all of this into a soft goodbye, a recap not of facts, but of feelings, and bring the journey back home to your breathing, your room, your night. For now, though, you can simply breathe and rest, and let the hidden states of matter slip quietly into the background, like stars behind clouds on a calm, dark sky. Tonight, we've walked a long, quiet road together. If you're still awake, you've come a very long way. If you're drifting in and out, that's perfectly fine too. This chapter is like the soft closing of a book that doesn't really end, it just rests on your chest while you sleep. Think back, just a little, to where we began. You were lying somewhere in bed, on a couch, maybe on a late-night train, and we started with the simplest picture: solid, liquid, gas. The mug, the drink, the steam. From there, we slipped into the glow of plasma, the ordinary air becoming star-like when it's heated enough. We watched lightning, neon signs, and the sun take on a new identity as examples of a state you don't usually hear about in school. Then we turned the temperature slowly down, like dimming the lights in a theater. We talked about what temperature really means, the frantic dance of particles that you never see. We crept toward absolute zero, towards stillness we can never quite reach, and discovered that near that horizon, matter reveals its quantum side. We watched Bose Einstein condensates appear, clouds of atoms losing their individuality, acting like one calm, shared wave. We saw superfluids that slip through tiny pores and climb their own container walls, as if friction has forgotten how to act. We saw superconductors where electric currents glide with no resistance, where magnets float in quiet defiance of gravity. Then, in a gentle reverse, we turned the temperature dial all the way up again and stood for a moment in the early universe, in the quark-gluon plasma, a hot, dense, nearly perfect liquid made of quarks and gluons, a brief echo of how everything once was. After that, we wandered through in-between worlds, liquid crystals in your screens, topological phases, whose properties are protected by deep, global patterns, spin liquids, and other exotic states that sit tucked away in research papers and experiments. We peeked behind the curtain at how scientists map all these possibilities, drawing phase diagrams like atlases of what matter can become, dot by dot, graph by graph. And then, in the last chapter, we step back even further, asking quietly what all of this means for how we see reality and how we live with not knowing everything. Now, here's the part where the story doesn't need to go anywhere new. It just needs to settle. You don't have to remember the names. You don't have to recite Bose-Einstein condensate, or quark-gluon plasma, or topological insulator to anyone. You don't need to carry a list of exotic states around in your mind like a set of flashcards. If all of those details blur into a soft impression that matter has many hidden ways of being, then the story has already done its job. Right now, the most important states of matter in your world are very simple. There is a solid supporting you. The bed, the couch, the seat. There are liquids flowing quietly inside you, keeping you alive without asking for your attention. There is a gas around you, filling your lungs, coming and going with every breath. Somewhere beyond your ceiling or the sky above, there are plasmas burning as stars. That's enough. And yet, tucked inside all of those familiar things, all of those hidden states, are times possible, asterisk. Under different conditions, different temperatures, pressures, fields, the same basic particles could rearrange themselves into something totally new. The universe you inhabit is not just a collection of objects. It's a collection of asterisk, asterisk possibilities, asterisk, asterisk, most of which you'll never need to confront directly. And that's okay. If that sounds like your own life, that's not an accident. You have the solid days, steady, structured, predictable. You have the liquid days, flowing, flexible, changing shape around whatever comes. You have the gaseous days, scattered, restless, fast-moving thoughts. And once in a while, there are phases of you that only appear under very specific conditions. Certain people, certain places, certain moments in time. You don't need to map them all at once. You don't need to name every version of yourself. You can let some of them remain hidden states, waiting to appear only when they're needed. Now, if you're still listening with a little bit of mental energy left, try a tiny thought experiment, very gently. Bring your attention to your breathing, not to change it, just to notice it. In and out. Air, a mix of gases, flows through you. Molecules bouncing and colliding, drawn in, shared with your body, and then released. Then, notice the weight beneath you. The solid beneath your body is made of atoms stacked into patterns, holding their structure because the particles inside are arranged in just the right way. It feels simple, dependable, immovable, even though, deep down, it's a busy lattice of motion. If you have a glass of water nearby, or you drank something earlier, think for a moment about that liquid, the way it flowed, the way it took the shape of its container. Those same molecules could, under other conditions, have been ice or vapor or something stranger, but tonight they were just a drink, quietly doing their job. In each of those cases, air, solid, liquid, there are countless microscopic stories playing out, and you don't need to keep track of any of them. You just live your life while they do their quiet work. In the same way, you don't have to hold all the cosmic and quantum details in your conscious mind. You can let them sink below the surface, like stones settling at the bottom of a lake. What's left at the surface is simple. You are part of a universe that is more intricate, more flexible, and more softly strange than any childhood diagram could capture. You are made of the same basic ingredients as stars, as plasmas, as condensates, as quark-gluon droplets. Right now, those ingredients happen to be arranged in the particular pattern we call you. That in itself is quietly extraordinary. And if that feels like too big a thought right now, that's okay too. You don't have to feel awe on command. You can just feel sleepy. Now here's the gentlest hook of all. You don't have to decide whether this story meant something profound tonight. You can let your brain file it wherever it wants, under science, under comfort, under nice. Voice in the background while I fell asleep. Maybe tomorrow you'll remember a little fragment. A liquid that climbs walls, a current that never fades, a tiny droplet of the early universe, or just the idea that matter has more ways of being than we see every day. Or maybe you'll remember nothing at all, just that you slept. Both outcomes are perfect. For a moment, bring your attention back to your own body. Notice your shoulders and whether they're tense or relaxed. If they're a little tight, you can let them drop just a small amount, like a solid melting a fraction of a degree into something softer. Notice your face, your jaw, your forehead, around your eyes. We carry a lot of invisible tension fields there. You don't have to force them to relax. Just notice and let a little of the effort evaporate, like steam drifting into the air. Feel the rise and fall of your chest or your belly as you breathe. You don't have to breathe deeply or slowly on purpose. Your body is already doing it for you, cycling air in and out without needing instructions. The room around you is probably quiet, or at least quieter than the day. Even if there are distant sounds, a fan, traffic, other people's lives happening somewhere nearby, they can blur into the background like soft noise on an old radio. Here, in this small space, you've been listening to the universe talk about itself through a sleepy science story. And now, it's okay to let the story end. If you've enjoyed wandering through these hidden states of matter, and you ever want to come back to this topic, or to another times, Whispering Scientist Times will be here, like a small light left on in a window. If you'd like, you can support this little channel with a like or a subscribe, but only ever if it feels gentle, never like a task. Think of it as leaving a bookmark in a book you might want to open again on another night. For tonight, though, there is nothing you have to do. No quiz, no exam, no need to hold on to any of this tightly. You can let your thoughts drift. Let the details dissolve, the way a solid dissolves into a liquid, the way a wave spreads out until it's just a calm surface again. The universe will keep its secrets and its phases and its patterns. The labs and colliders and telescopes will keep watching, mapping out more of what matter can do. You don't have to. You've done enough for today. Thank you for spending this time here, for letting your mind wander through solids and plasmas and condensates and all the quiet, hidden states in between. Wherever you are in bed, on a train, on a couch, with a fading cup of tea, I hope you feel safe and I hope you find rest. So, from this little corner of the cosmos, from this soft, whispering scientist voice to you, good night, sleep well. May your thoughts settle like calm matter finding its most peaceful state, and may you drift, gently and easily, into whatever dreams are waiting for you on the other side of this sentence.